Okay, I'll get started for today's class. The last few classes, last handful of classes, we've been discussing energy and we've been discussing momentum. We've talked about the transfer of energy. We talked about the transfer of momentum by forces. Actually, the transfer of energy and the transfer of momentum are so important, we give them special names: work done, impulse given. And we've talked, perhaps most importantly, probably most importantly, about the concepts of energy conservation and momentum conservation. It's really interesting to me that beneath all the motion and the action that forces are causing, there's this sort of underneath or beneath level in which energy and momentum, despite all the changes, are being conserved. And so it gives us a new way of thinking about, a new way of looking at motion in terms of energy and momentum conservation that complements that sort of perspective about forces and how forces influence and forces act on objects. Okay, today's class, I really want to talk about one sort of quantity or one sort of subject, and that's really the application of energy and momentum conservation to what we call collisions, where one object strikes another object. And we're going to talk about a number of different types of collisions between objects. We're going to talk about head-on collisions, glancing collisions. You'll learn what those words mean in physics. We'll talk about elastic, inelastic collisions. You'll also learn what those words mean in physics. And so let's get on with this. But before I get on with it, I just wanted to stress the importance of collisions, colliding things in physics. One example of how important collisions are in physics is that 20 years ago, the world's biggest collider of protons with protons was built in Switzerland. It's a $10 billion machine at the time it was built. It had 100 countries collaborating in it. It had 10,000 scientists working on it. It's a massive thing. You see this aerial shot of where the collider is located in Switzerland. It's actually partly located in Switzerland and partly located in France. It's so big. And its circumference is 27 kilometers. So that must be like 15 miles, something like that. And it's buried 500 feet below the ground in a tunnel. And in this collider, there are, if you look down at the bottom here, there are protons traveling at almost the speed of light, traveling in a clockwise direction. Protons traveling at almost the speed of light in a counterclockwise direction. That's the red and the green here. And they are collided at certain locations. And the scientists look at the debris or the wreckage from these collisions, and they explore the nature of matter by looking at the debris, the wreckage from these collisions. And there's an immensely famous result that came out of these collisions with this $10 billion collider. So my perspective, it was kind of money, seems a lot of money, right? $10 billion, but it had a really, really important result. And that result actually came by applying energy and momentum conservation to the collisions. And that result was a discovery of a completely new particle in nature, a completely new type of particle in nature that actually gives mass to all the other particles in the universe. So, it gives mass to protons and neutrons that you know about, gives mass to electrons, you know about those too. And all the other particles in the universe, it gives mass too. So it was literally a huge discovery in physics. It's called the Higgs particle. You may have heard it. And I think that's the reason that Lady Gaga came to class, 2 classes in a row, because, you know, collisions have been so important in physics, so important in nuclear and particle physics and atomic physics, that she's come to this class to learn about collisions. This is inside the tunnel, by the way. So here she is inside the tunnel. There are protons approaching from the far end of the tunnel, protons coming into the shot from the near end of the tunnel, and those protons collide, and we look at the wreckage. Okay, so I want to move on to talk about collisions. And the first few slides I've got are really some general remarks about collisions. And then we're going to look at particular examples of collisions. So most of the class is working through examples, particular examples of collisions. So first question, you know, we're going to imagine 2 objects colliding. Maybe it's 2 everyday objects. Maybe my car collides with somebody else's car, which has happened. So that's an example of an everyday collision. Or maybe it's the collision of a proton with another proton in that $10 billion accelerator. That would be a collision between elementary or fundamental particles. So is momentum conserved in those collisions? Well, if you remember back to last class, we talked about when momentum is conserved and when momentum is not conserved. And momentum was conserved if you have a system on which no external forces are acting, and only internal forces are acting. So in this slide here, let me get my pen running. If you think of the Earth and the apple together, and their interaction, their gravitational interaction, their gravitational force, that's a complete system. And together, the Earth and apple conserve momentum. If you thought separately about the apple or separately about the Earth, the apple separately doesn't conserve momentum. The Earth separately doesn't conserve momentum. But together, the entire system of the Earth and apple conserves momentum because there's internal forces between the apple and the Earth, but not external forces. The same thing was true in this picture on the right. This is the book sliding across the desktop. If you think about the book and the Earth together, that system conserves momentum. If you were to think about the book separately or the Earth separately, they individually don't conserve momentum. That's because the force between the book and the Earth, a frictional force, is an internal system, if an internal force if you're thinking about the book and the Earth as a system, but an external force if you're thinking separately about the book or separately about the Earth. So in collisions, supposing 2 cars strike one another, or 2 protons strike one another, the forces that are acting between the 2 cars, the forces that are acting between the 2 protons are internal forces. If you're thinking about the 2 cars as a system or the 2 protons as a system. And so in the collision overall, between 2 protons, between 2 cars, momentum is conserved because the forces between the cars or the forces between the protons are internal forces. And so we can apply momentum conservation to all collisions we're talking about. What about energy conservation, specifically kinetic energy conservation, the kinetic energy associated with the motion of the 2 colliding cars or the 2 colliding protons? Is that conserved? Well, that depends. We're going to talk about collisions where it is conserved, and we're going to talk about collisions where it isn't conserved. The guide to whether it's conserved or not conserved is really whether significant energy is dissipated in the collision in other forms. So in the collisions of a pair of cars, right, there might be damage. That's dissipating energy into damaging the cars. There might be heat. That's dissipating energy into heat in the collision. There might be the noise of the collision. That's dissipating energy into the noise associated with the collision. If that dissipation of energy into damage or heat or noise or other forms, if that's significant compared to the original kinetic energies of the colliding cars or the colliding particles, then that would, then kinetic energy is not conserved because you've dissipated significant amounts of it. And so you can't apply kinetic energy conservation. But in other collisions, and the famous example is a pair of colliding billiard balls or other objects, then in that case, if there's no significant dissipation of energy in forms like damage or heat or noise, then kinetic energy is conserved. And we give those two cases specific names. Elastic collisions are where the kinetic energy is conserved, and inelastic collisions are where the kinetic energy is not conserved. And so we'll be investigating both elastic and inelastic collisions. And so just think of elastic and inelastic as our code words for saying kinetic energy was conserved or kinetic energy wasn't conserved in this collision. Okay, now I want to just run through a little bit of collision terminology on this side, some collision language. We're going to talk about what we call perfectly elastic collisions. So those, just to stress, are those collisions in which both momentum and kinetic energy are conserved. And we're going to talk about inelastic collisions. Those are collisions in which momentum is conserved, but kinetic energy is not conserved. So those are the two basic categories of collisions. We'll also talk about a class of collisions that are called perfectly inelastic collisions. Now, what does that mean? That's a little bit more subtle. It means, well, momentum's conserved in all collisions. They're inelastic, so kinetic energy is not conserved in these collisions. But in perfectly inelastic collisions, the two colliding objects, say the two cars or the two colliding protons, they stick together. They join together. They form one object. And so that's perfectly inelastic collisions. And then we're going to talk about head-on collisions and glancing collisions. Head-on collisions are collisions where all the action is in one dimension. So the two colliding cars approach one another along a line, and then when they collide, they bounce off one another along that line. Everything happens in one dimension, and we can use plus and minus signs for the directions of the colliding objects. In glancing collisions, on the other hand, then the action happens in two dimensions. And you could imagine two cars glancing off one another at angles where they span a two-dimensional space now. You could imagine two protons colliding with one another where the outgoing and incoming particles spread out over two-dimensional space now. And then you have to use vectors to describe the directions of the incoming particles, the outgoing particles from the collision. You can't use the plus and minus signs anymore. Only use the plus and minus signs for directions when you've got head-on collisions along one dimension. So that's the language we use for collisions. That's our collisions terminology that is going to come up time and time again as I work through some examples now. Okay. So first example. And I think I've ordered, there's three examples here. I've ordered these three examples probably in the direction of sort of increasingly more complicated. And I think you'll see that as we work through these examples. So this first example is perfectly inelastic head-on collision. Now that's a fairly long description, but those words mean something, and we've just learned what those words means. Perfectly inelastic means this is a collision conserving momentum. This is a collision that doesn't conserve kinetic energy. And it's a collision in which two objects collide and stick together. And the head-on means that all this action of approaching one another, colliding, sticking together, happens along a single line, along a straight line. And so these code words are handy because they sort of codify this description of what's going on into this simple phrase. Perfectly inelastic head-on collisions means a lot of things about kinetic energy, momentum conservation, about the collision being along one dimension, and about the fact the objects are going to stick together. Okay, so here's a picture of the situation. And normally when we draw collisions, we draw pictures where we might draw like before and after the collision. And so upstairs here is the picture of the movement of the colliding objects before the collision. Downstairs, movement of the colliding objects after the collision. And in this particular example, I've got this green car on the left, blue car on the right. So initially, you see them approaching each other along a line, and I've even denoted the velocities at which they're approaching. So I've called V with a subscript 1 and 2, the velocity of the green car, and V with a subscript, it wasn't a subscript 1 and 2 on the green car, it's subscript 1 and I, for initial on the green car. And then there's a subscript on the blue car's initial motion. It's a V with a subscript 2 and I. And then downstairs here, after the collision, so these cars have now stuck together in this perfectly inelastic head-on collision, there's a single velocity of the two cars because they're stuck together. They are the wreckage. And I've just called that V subscript F. And so when I put the little subscripts on the V's before and after the collision, I was trying to use them to denote the different categories of V's. So the 1 and 2's refer to the car on the left and the car on the right. So this is car number 1 on the left. This is car number 2 on the right. And then they're going to stick together. And so the subscripts 1 and 2 refer to the two cars. The I's refer to the fact that this is the initial situation before the collision. And the F's refer to the fact that this is the final situation, final velocity after the collision. So I'm using I's to denote initially and F's to denote finally. Okay, so that's the picture, and that's, always an important part. And then I'm going to turn that picture into equations that describe the collision. And in this case, I can build one equation. I can build one equation because I've got momentum conservation, but I don't have kinetic energy conservation. So there's only one conservation law. I'm only going to get one equation here. And so the equation is basically, as I've written, that the initial momentum, remember P is the symbol for momentum for some reason, the initial momentum, Pi, equals the final momentum. And from the definition of momentum, being mass times velocity, I can write down the initial momentum over here on the left is partly carried by the green car, car number 1, is partly carried by the blue car, car number 2. It depends on the masses of the cars and the velocities of the cars. And then after the collision, I can write down the expression for the momentum. Now is the momentum of the wreckage, which is the sum of the masses of the two cars, the green one and the blue one, and the speed of the wreckage, the velocity of the wreckage. And so this is expanding momentum conservation for our particular situation of two cars colliding, sticking together. This is the formula that describes these perfectly inelastic head-on collisions. And this is the formula that we'll use to analyze perfectly inelastic head-on collisions. And as I say, in this case, kinetic energy wasn't conserved. Kinetic energy was lost, and it was lost to damage, to noise, to heat. And so we can't apply kinetic energy conservation. Okay, so let's work an example of a perfectly inelastic head-on collision. And so in this example, we're told that we've got an arrangement of 3 rail cars, basically, 3 identical rail cars. And initially, one of them is moving towards the 2 others, and it's moving with the speed of 2 meters per second, and it's going to collide with the others that are stationary. And so we're told the motion of the first one, we're told it's going to collide with the stationary other 2, we're told the masses of all the rail cars, they're all the same. And we're going to figure out a couple of things after the collision has occurred. And in this collision, if it's perfectly inelastic, these colliding rail cars are going to stick together. We're going to find out the final speed of the 3 rail cars as they move off together, and what kinetic energy was lost to damage and heat and noise in the collision. So we're going to do those 2 things. Okay, so the first thing I would normally do in this type of problem, and I always say this, is that I'm going to make a sketch. And in this case, I'm going to sketch the situation before the collision and after the collision, and I'm going to add to that sketch. I'm going to add to that sketch the things that I know, the things that I want to find out, and also I've added to this sketch some basic formulas, equations about the momentum in the collision. So over here in blue on the left, this is before the collision, I've got the single moving rail car. So its mass, I've called it uppercase M, and its speed, I've called it, that was 2 meters per second, we were told that. And then over here on the right is the 2 rail cars that were initially stationary. And I'm thinking of them as, you know, a combined 2 rail car system. Their mass is then 2m, 2 rail car masses, and their speed was, their velocity was 0. So that's the situation before the collision. And then after the collision, look what's happened here. The 3 rail cars have stuck together. They've coupled together. They're now moving as one. And so we've now got one moving object. Its mass is 3m. That's the final mass. And its velocity, well, we got to figure that out. That's a job to figure that out. Okay, so that's the picture, and that's the annotation of the picture. And then I added just some remarks to remind me about momentum. The momentum before the collision, in general, would be the sum of the momentum of that single moving rail car and those 2 other rail cars. And the momentum after the collision, well, now we've just got a single moving object, and it would be the momentum of that single moving object made of the 3 rail cars. And so I just reminded myself about the momentum before and after the collision. Okay, so let's go on and do the calculation. Okay, so the first calculation I did was to find the final speed. The final speed of the 3 moving rail cars. And it's based on, as we said, momentum conservation. So the basic idea, I wanted to stress it here, that's why I rewrote it, is that in this collision, you know, lots of things happen. There's forces, there's interactions, there's damage and heat and noise, but one thing that doesn't change is the momentum. The initial momentum equals the final momentum. So that's my starting point. And then I just fed in those equations for the initial and final momentum. Initially 2 objects, finally 1 object. The m's in this case, this is a nice example because the 3 objects involved all have identical masses. So actually I can just cancel them all out in this momentum conservation equation. So, you know, that whoever asked me that question in the first place, I wonder, were they trying to trick me about giving me the mass? Because I didn't really need the mass. All I needed to know was the masses are equal. So the masses cancel out, and if you then divide by 3, you get an equation for the final speed in terms of the initial speeds of the single rail car and the pair of rail cars. Now, the initial speed of the single rail car was non-zero. It was 2 meters per second. It's down here. The initial speed of the pair of rail cars, they were actually stationary. So that was 0. So that piece went away. But you could imagine other problems in which they were both moving before the collision. And this equation would solve that too. You just put in whatever speed you have for the colliding systems, you're going to get the final speed of the combined system. In our case, the speed goes from 2 meters per second of the single moving rail car to just 0.67 meters per second for the 3 moving rail cars. And so we solve that problem relatively simply by applying momentum conservation. Once you know the speed of all the objects before and after the collision, which we now do, we can go on and solve the second part of the question. And that was to calculate the changing kinetic energy. And so that's what I'm doing on this slide. And to calculate the changing kinetic energy, that change is just the difference between the final kinetic energy of the 3 cars moving together and the initial kinetic energy of the single car and the pair of cars. And then all I had to do was to fill in the definition of kinetic energy, which we introduced a while back. Remember, it's half the mass of the moving object times the square of the speed of the moving object. So I just fill in half the mass of the moving object times the square of the speed of the moving object for, you know, each of the 2 objects before the collision and the single object after the collision. So here's after the collision, here's its mass, 3m, and here's its speed, f, vf, and then here is the kinetic energy before the collision, kinetic energy of the single moving car, kinetic energy of the pair of joined together cars. Now, this is actually going to be 0 again, so this piece will go away, but I've written it out because you could have a problem in which both things were moving beforehand. Anyway, to come up with the answer to the changing kinetic energy, I made life a little simpler for myself by spotting the m's are common factors in each of these terms. I poured the m out front of the parentheses. And then I just plugged in all the numbers. Plugging in the m, plugging in the speed of the cars moving together after the collision, the speed of the single car before the collision, the stationary nature of the pair of cars before the collision. And if you plug in all those numbers, you get an amount of energy that got released in this collision that is large. It's about 38 kilojoules, 38,000 joules. And it actually was about 2/3 of the kinetic energy before the collision. So a lot of energy was released in this perfectly inelastic collision to damage and heat and sound and so forth. Okay, let me show you a demonstration of this collision because I actually I went downstairs to the lecture room and I reproduced this collision. Let me show you that. So I'm going to share a different screen. Okay, so I hope you can see this second screen here. And what you're going to see is a single rail car traveling at 2 meters per second, colliding with two other rail cars, stationary, and then the wreckage, the joined wreckage of the three rail cars moving off at a speed of 0.67 meters per second. So this is an exact reproduction of the problem that we've just worked. And you see that after the collision, the three together are moving much more slowly than the single one was moving before the collision. It's so short, and it took me so long to do that, that I'm going to play it again. So before the collision, a single moving rail car, collision, after the collision, three moving rail cars stuck together. That moment of the collision, right, that's where the forces are acting. That's where work is done. That's where impulse is given. But in solving the problem, we just worried about before and after. That's a nice feature of applying energy and momentum conservation laws. Okay. Well, that was fun, kind of, I guess. Now I want to go back to my slides. Let me try and share those again. And I want to talk about what might seem like a rather unrelated topic, but it turns out to be a rather related topic. So have you ever wondered, how does a rocket move? Have you ever wondered, how does a squid move? And maybe you haven't wondered how a squid moves, but we're going to wonder how a squid moves in this slide and the next slide. I've got to get the chat back up, sorry. Okay, there's a question about in the chat about the last example about if it were not perfectly inelastic. I'm going to show you soon an example where it is not perfectly inelastic. It's going to be elastic. But that world in between perfectly inelastic and elastic is a difficult world of problems to solve. So it's actually a really good question, and we're going to actually not go there. So that was a great question, and it actually brings up the point that collisions in general can be very complicated. And we're going to stick to a limited set of collisions that we can readily solve. Okay, but anyway, how does the squid move? Well, you can think of the way the squid moves by thinking about momentum conservation. So here's a picture of the squid, and the way the squid will move. Let me get the pen going. So as squid is going to move up towards the top left here, the way it moves is by shooting water down towards the bottom right. So imagine you are the squid and you're just floating there in the ocean and you want to go up to the top left. Well, you squirt water down to the bottom right. From the momentum perspective, what's happening is initially you have no momentum. You're a squid and you're not moving. You have no momentum, you want to move. So what you do is in your system, which is you and the water around you, you squirt some of that water in one direction and you head off in the other direction. You acquire some momentum. The water acquires some momentum, but those momenta are equal and opposite. And so you started with zero initial momentum in this system of the squid and the water. You ended up with zero final momentum in this system of the squid and the water. But within the system, due to internal forces within the system, the squid now has its momentum and the water has its momentum, and they're equal and opposite momenta. And that's how squid moves. Similarly for the rocket, right? How does a rocket move? Well, supposing you're the rocket on the launch pad and you want to launch yourself upwards. How are you going to move upwards? Initially, the rocket and the fuel in the rocket has no momentum. So how's it going to move? The way it moves is to move the rocket upwards, it shoots the fuel downwards. And so that initial system of rocket and fuel had zero momentum, and that's the system. And to move the components of the system, you exert internal forces that push the rocket up and push the fuel down. And in that way, you can move. So again, the rocket and fuel had zero, the rocket and fuel had zero momentum to begin with. I've done it again. The rocket and fuel had zero momentum to begin with. They have zero momentum after the launch. But that zero momentum after the launch, the components of the system, the rocket has some momentum upwards, the fuel has some momentum downwards. It's just the sum of those momenta is now zero. So that's how they get themselves moving. Now, if you think about this, both this situation with the rocket and the situation previously with the squid, they are kind of the reverse of perfectly inelastic collisions. Here you're starting with one object stuck together and parts of it are heading off in opposite directions. That's the reverse of the two cars colliding together and moving off as wreckage. And so this system with the rocket and the fuel and the system with the squid and the water is very much like that perfectly inelastic collision, but in reverse. Okay, so let me move on. So that's a question about a bullet fired from a gun and momentum and energy conservation. And it actually it's the same situation really as the water fired from the squid, energy momentum conservation there, and the fuel fired from the rocket and energy momentum conservation there. And we saw that all those situations are really like the collision of the single rail car with a pair of rail cars that stick together. They're reverse, perfectly inelastic collisions. And in all those collisions or reverse collisions, momentum is always conserved. Kinetic energy is not conserved. And so the correct answer for that is that the magnitudes of the momenta of the bullet and the gun are the same. They're equal and opposite in directions because you know, right, if you've ever fired a gun, I did it once and I'll never do it again, the gun heads in the opposite direction to the bullet, and it heads in the opposite direction to the bullet with the same momentum that the bullet had, so it recoils. But kinetic energy wasn't conserved in that. And you can see it, obviously, when you fire a bullet from a gun, or the squid fires water and starts moving, or the rocket fires fuel and start moving, because there's no kinetic energy to begin with of the bullet in the gun, or the squid in the water, or the rocket in the fuel. And then suddenly there is kinetic energy, because both the bullet in the gun are moving, both the squid in the water are moving. Okay, let's move on. Perfectly elastic head-on collisions. Let's deal with this situation. So here's my sketch of perfectly elastic collisions. I'm going to imagine two billiard balls striking one another and then bouncing off one another. So upstairs here is before the collision, they're heading towards each other. Downstairs here is after the collision. And again, there's some key words in here. Perfectly elastic means kinetic energy and momentum are conserved. Head on means all the action is taking place along a straight line. It takes place in one-dimensional. Takes place along that straight line. So in this case, right, there's two equations that we can write down. In the last case of perfectly inelastic, there was one equation we could write down. Now we've got momentum conservation as before, but we've also got kinetic energy conservation. So in this case, the momentum conservation, if I fill in the definition of momentum, gives me this little formula here. I'll say a bit more about it in a moment. And the kinetic energy conservation, if I fill in the definition of kinetic energy, 1/2 mv squared, gives me this little equation here. So let me say a few words about these two equations and the notation on the quantities in these equations. So I've got two objects, and I called them mass m1 and mass m2. Objects 1 and 2 with masses m1, m2. They had some initial velocities. I called those initial velocities v1 initial for the velocity of the blue ball, the one we're calling number 1, and v subscript 2i for the velocity, the initial velocity of the second ball, the ivory one over here on the right. And so I'm using the subscripts to denote which ball it is with 1 or 2, and I'm also using the subscripts to denote before and after. So after the collision, my velocities are v1f for the final velocity, v2f for the final velocity. And so that's my notation that makes these equations for momentum conservation and kinetic energy conservation look kind of, I don't know, complicated or ugly, but it's just because we've just been blasted with subscripts, right? At their heart, there's nothing complicated about either equation 1 or 2. This is just equation number 1, the sum of the initial momenta equals the sum of the final momenta. And equation number 2, this is just the sum of the initial kinetic energies of the two masses is equal to the sum of the final kinetic energies of the two masses. And that's energy and kinetic energy and momentum conservation. Okay, that was fun. Now, when we solve these type problems, you can see you've got two equations to solve these problems with. We tend to use actually a different version of these. It's a little bit messed up, this slide. I just know I'm going to have to fix this for you. I don't know what I did here. This is an M, this is a V, this is an M, this is a V. This was an M. Okay, well, we've got the momentum conservation equation. That was this guy here. That's as we wrote it on the last slide. But actually, I've rewritten the kinetic energy conservation equation. And you can rewrite it with some algebra. I'm not going to discuss this algebra. It will take, it'll take me the rest of the class probably. It's not hard, but it's just time-consuming and laborious. You can rearrange the energy momentum conservations for a second equation that looks simpler than the kinetic energy conservation equation. It's this one here. And what this one here is saying is that the velocity at which the objects approach one another before the collision is equal and opposite to the velocity at which they recede from one another after the collision. So if you want to imagine this, imagine that you're riding on, imagine I'm riding on the blue ball on the left. I see the ivory ball approaching me, and I see it approaching me with this difference in our velocities. So that's the velocity of approach. I'm riding on the blue ball again as it moves away from the collision, and I see the ivory ball receding from me, and its recession is this guy here. Now, one of them had a plus sign, one of them has a minus sign. That's because here they're approaching one another on the left, here they're receding from one another on the right. It just says it's just a relationship between the velocity of approach and the velocity of recession. And so that's actually a handier pair of equations to use in solving these collisions than the original equations of kinetic energy and momentum conservation. Okay, so let's solve a problem then. We got in this one we got so this is an example of perfectly inelastic head-on collisions. And we got a billiard ball that's initially traveling at 1.35 meters per second. It makes a head-on collision with another identical stationary billiard ball. And we got to find the speed of the two billiard balls after the collision. Now this one, we're going to have to find two speeds of the two balls after the collisions. And we're going to need those two equations to find the two speeds. We're going to end up with a two equations and two unknowns type problem. And that's something that you can do with these perfectly elastic collisions, because you've built two equations out of two conservation laws, the kinetic energy and momentum conservation. Okay, so here I'm going to apply those equations, the energy and momentum conservation laws, which gave us the momentum conservation equation. That's the upper one here. If I do this one more time, I'm really going to lose it somehow. I've got these two equations. Here's the momentum conservation one. And here's the one that was this combination of momentum conservation and kinetic energy conservation that allowed us to rearrange that the approach velocity equals the recession velocity. Okay. So I'm just going to plug in to these general equations, this one here and this one here, my particular situation. And my particular situation that I'm going to plug in is that my masses for these pair of billiard balls are actually equal to one another. So these M1s and M2s, they all cancel each other out because they're all the same. And I'm also going to plug in the fact that, well, I know the initial speeds of the two balls. V1I is 1.35 meters per second. V2I is 0. So this left-hand side in the momentum conservation equation is 1.35 meters per second. And then I'm going to do the same thing down here. I know that V1I is 1.35 meters per second. V2I is 0. And so this also is 1.35 meters per second. And what I've done then is make two new equations. I labeled them 1 in green here and 2 in red here. That are two equations with two unknowns, the two final velocities, V1F, V2F, that I can go ahead and solve. Go ahead and solve for those two individual velocities. And so that's what I've got out of applying the physics of energy and momentum conservation, is a pair of mathematical equations. Suddenly I've become like a math major, which would be a very awful thing for me, but I've become a math major and I've got to solve now two equations with two unknowns. And I just rewrote from the last slide these two equations. And if you look at them, one of them says that the sum of the velocities after the collision is equal to 1.35 meters per second. And the other one actually says that the difference in the velocities, v2f minus v1f, that is also equal to 1.35 meters per second. So how can that be? Let's work out the solution. Well, the easiest way to solve this pair of simultaneous equations for the two unknowns is no, look, in one case, you've got a positive v1f, the other case, you've got a negative v1f. If you add the two equations together, which is what I'm going to do over here, the v1f positive, the v1f negative will cancel each other out. You'll just be left with two v2f's. And so that's what I did here. This is the sum of the two equations. I sum the left-hand side, and I sum the right-hand side. And it says that 2.7 meters per second equals twice the final velocity of object number 2, so that the final velocity of object number 2 must be half that, 1.35 meters per second. Then I can go back to either of the first two equations. I went back to number 1, but I could have equally well gone to equation number 2. Knowing v2f, I can plug that number in, 1.35 meters per second, and figure out what v1f must be. And you can see here, if v2f is 1.35 meters per second, and the left-hand side is 1.35 meters per second, then v1f must be 0. And so we solved the problem. We found the two final velocities of the billiard balls. And so that's an example of solving an elastic collision where you've got two equations from energy and momentum conservation, and you can solve, therefore, for two unknowns. I want to show you a demonstration of this. Again, I went to the lecture room and I set up exactly this situation. So let me get to the next slide. And we're going to watch this second video, which is going to be a perfectly inelastic collision. Sorry, a perfectly elastic collision of two equal mass objects. I'm doing it in slow motion again because they're short videos and I want to stretch them out. And you see all the action in slow motion. So I've got one moving object to begin with. Strikes the second moving object, and that second moving object moves off. And that's exactly the situation we just calculated. Basically, the velocity of the first moving object is kind of handed over to the velocity of the second moving object. The initially stationary moving object now becomes moving, and the originally moving object becomes stationary. And that's a feature of the collision of two equal masses when you have one that is stationary. They basically replace one another. The one that was stationary becomes the moving one. The one that was moving becomes the stationary one. Okay. Stop sharing that and let's get back to the slides. And we'll work one more example, I think, is the plan. Okay, last example, I want to look at a perfectly inelastic glancing collision. So you might remember our first example was perfectly inelastic head-on collision. So this example and the very first example have something in common, which is that they're perfectly inelastic. So they both involve two objects that are moving, collide, and get stuck together. The wreckage is stuck together. But they are different in the fact that in the first example, all the action was along a single line. So one-dimensional collision, head-on collision. In this example, the action spans two-dimensional space. It doesn't occur along a single line. And so the reason I'm including this example is an example where now we can no longer indicate the directions of the moving objects with plus and minus signs. we have to indicate the direction of the objects or the momenta with vectors. We've got to work with vectors. Okay, so here's the perfectly inelastic glancing collision, and this is actually the situation that happened to me. And here in this picture, we're imagining that collision. I've got to get my pen working again. There's a car over here on the left that's traveling to the right. It's an ivory colored car. And there's a van down here that's traveling upwards, a blue colored van, and they strike one another in this intersection. And they've struck one another and they've stuck themselves together. And over here on the top right is the wreckage moving off. And we've pictured also on the sketch, you know, the initial velocity of car number one. So this is V1I. The initial velocity of van is number two, so it's V2I. And then the velocity of the wreckage, that's VF. So we're using this notation that we kind of used before for the two initially moving objects and then the single final moving objects. And as a reminder, in perfectly inelastic collisions, in inelastic collisions actually in general, momentum is conserved, like in all collisions, but kinetic energy is not conserved. Kinetic energy is released, in this case, into damage and heat and noise. So we're only going to have one equation to apply, and here it is. It's momentum conservation. This is that the initial momentum, I'll call it PI, of the two moving cars equals the final momentum, PF, of the wreckage. And all I did was expand the initial momentum in terms of the definition of momentum and the fact that I've got two moving objects over here on the left, and the final momentum, again, in terms of the definition of momentum and the motion, the velocity of the moving wreckage. And so you get this little equation here. And we met a version of this equation before for the perfectly elastic head-on collisions, but the difference was that now we've got to handle these vectors that live in this two-dimensional world of left and right and up and down on the sketch or on the slide. And so we've got to deal with vectors rather than plus or minus signs for applying momentum conservation. Okay, so let's look at an example of perfectly inelastic glancing collisions. And so in this example, we're being told the information that we need to solve the problem. The problem is going to be the problem of what is the speed and the direction of the wreckage after the collision. So we're going to try and figure out the speed and direction of the wreckage here. And we're told the initial speed of the car coming in from the left, the initial speed of the velocity of the van coming up from the bottom, and we're told their masses. We're going to need their masses too. And they're unequal masses. So that's the information we're given, and we're going to find this final velocity here by answering what is the speed, what is the magnitude, and what is the direction, what is the angle. And I'm going to do it in a couple of steps, basically. And the first step I'm going to do is actually to figure out the momenta of the car and van before the collision, their initial momenta. And I'm going to figure out that initial momenta in component form, in X and Y component forms. So that's going to be my first task. This is probably the biggest task in this problem. Once we got these momenta of the car and the van before the collision in X and Y component language, we can figure out the final momentum and answer the question is, what is the final speed? What is the final direction of the wreckage? Okay, so first of all, I'm just picturing it again here, making a nice, clear diagram of what's going on. And I didn't mean to do that, but that's okay. So here's my picture. That's not what I want to do either. Here's my picture. I've got this blue arrow indicating the blue car's momentum. I've got this green arrow indicating the green van's momentum. You know, I've labeled them P1 initial, P2 initial for car 1, van 2, and the initial momenta. And I've written down the fact that I know the speed of the car, velocity of the car, and I know the mass of the car. I know the velocity of the van, and I know the mass of the van. Okay, so now I'm going to find out the X and Y components of the momenta of the car, which is in blue here because there's a blue car, and the van is a green van, maybe. Here's the momenta of the green van. And so I'm going to call those momentum components P1IX, P1IY. That's a whole collection of subscripts. 1 for the car, I for initially, X and Y for the horizontal and the vertical components. And likewise down here, P2IX, P2IY, 2 for the van, I for initially, and X and Y for the horizontal and vertical components. The momentum, remember the momentum, here it is mass times velocity. The X component of momentum is the mass times the X component of velocity. The Y component of momentum is the mass times the Y component of velocity, and so on. So I've used the definition of momentum here. And then I've filled in the masses. So here are the masses of the car. Here are the masses of the van, 2,000 kilograms and 3,000 kilograms respectively. And then I've multiplied by the components of velocity. And I could do that straightforwardly because look, for the car, it's just traveling towards the right in the positive X direction. It doesn't go up or down. So all its velocity is in the direction towards the right. So that total velocity is v1x. There's no velocity in the y direction. There's v1y is 0. And similarly, for the van, right, it's traveling in the positive y direction, upwards in my picture. So all its 20 meters of velocity are in the y direction, and there's no component horizontally. Its horizontal velocity is 0. And so I didn't need to do, in general, you'd need to work with sines and cosines to find the x and y components of the velocities from the velocity vector. In this case, it's easy to see that one's horizontal, positive x direction, one's vertical, positive y direction. Just use those. That's what I did. Anyway, that told me that the momenta components for the car, x component is 50,000 newton seconds, y component is 0, x components and y components for the momentum of the van is 0 for the x component and 60,000 newton seconds for the y component. So we can visualize those momentum vectors. We've quantified those momentum vectors. Okay. Okay, so now what I'm going to do is we now know the car's initial momentum in X and Y component language. We know the van's initial momentum in X and Y component language. Let's figure out the wreckages and final momentum in X and Y component language. And now this has become pretty easy. So the momentum of the wreckage, which are pictured here in red, so this is the wreckage. This is the wreckage momentum vector, is the sum of the momentum vectors of the car This is the car's initial momentum vector in blue, and the van's initial momentum vector. Here it is in green. Those two vectors add together. Remember, the second vector sits on its toes are on the head of the first vector, and the resulting vector, the sum, runs from the tail of the first to the tip of the second. And so this is a picture of the final momentum of the wreckage. And then we can calculate the components of the final momentum. There'll be PFX, so that'll be the horizontal component. There'll be PFY, that'll be the vertical component. By simply adding up the X components of the car and the van's momenta before the collision, adding up the Y components of the car and the van's momentum before the collision. So those are the P1X, P2, so P1IX, P2IX from the last slide. They're the P1Y, P2IY from the last slide. And so I just filled in the numbers for those. Remember, for the car, it's moving in the positive X direction. So it has a component of momentum in the X direction, 50,000 Newton seconds, but nothing in the Y direction. And the reverse was true for the van. It was moving in the positive Y direction. It had a component of 60,000 Newton seconds momentum in the Y direction, but nothing, absolutely nothing in the horizontal direction. And so I add these up, and here are our two momenta. These are the X and Y components of the momentum of the wreckage. And so now we know the momentum of the wreckage. Last slide coming up on this problem. If I can ever get to it, that is. Okay, so let's now calculate. We know the momentum of the wreckage in X and Y component form. Now let's calculate the speed of the wreckage and the direction of the wreckage. There should have been a comma up here, I guess. Calculate wreckage speed direction. Okay, so first thing is that remember that the speed or the velocity is related to the momentum. So we can turn the momenta into velocities using the definition of momentum. So we're going to remember that. And also remember that if we want we want to actually figure out the magnitude of the velocity and the direction of the velocity. So here's the velocity vector itself, and here's its direction and its magnitude. But what we'll first have to figure is its components, because we know the components of the momentum of the wreckage. And so there's going to be two little steps on this slide. So let's just do those. Here's the first step. So all this step is, it's pretty straightforward, I think. I'm just going to calculate the X and Y components of the velocity of the wreckage, knowing the X and Y components of the momentum, which we calculated on the last slide, and just dividing that by the mass of the wreckage based on this definition of momentum. And so I plugged in the numbers, and here are the X and Y components of the wreckage. 10 meters per second X component, 12 meters per second Y component. Now I know the X component and the Y component of velocity. I can just change the language to magnitude and direction language and answer the question finally. So let's do that. And here I'm doing that downstairs. I'm going to calculate on the first line, I'm going to calculate velocity. Second line, I'm going to calculate direction. Calculate the magnitude of the velocity or the speed and the angle with respect to the horizontal. So the speed or the magnitude of the velocity, we can get from the square root of the sum of the squares of the x and the y components. And if I plug in the 10 squared plus the 12 squared, I get 15.6 meters per second. And then for the direction, if I want the direction with respect to the horizontal, which is what I'm indicating here, I'm going to take the inverse tangent of the opposite, which is the vertical component, divided by the adjacent, which is the horizontal component, this little guy here, and that gives me 50 degrees. And we've answered the question. Okay, let me end there. Sorry, I went over by a minute. We looked at collisions and kinetic energy and momentum in collisions, and we worked through several examples of collisions. Head-on, perfectly inelastic, head-on, elastic, and then glancing, perfectly inelastic. And those are sort of classic examples that we can do in general physics. And next week, we're going to move on to a new